Yeah, thanks a lot. Thanks a lot, Akil, for the invitation. Very happy to be back in Chicago. Yeah, so indeed, this is the first of a series of 4 lectures I will give on theory of analytic prismatization. This is a joint work in progress with Johannes Anschütz, Juan Esteban Rodriguez Camargo, and Peter Scholze. And so this will be complemented by a series of lectures by Maximilian on the analytic syntomification. And so this joint project has somehow had basically like 2 main motivations. One was p-adic. Please tell me if I have to write bigger. P-adic Hodge theory of rigid analytic spaces. And another important motivation for us was the geometrization of, or let's say the geometric aspects of p-adic Langlands program. But for depending on the perspective that you adopt, you can motivate our constructions a bit differently. For time reasons, I decided to focus on this first motivation in this series of lectures, but I'm happy to discuss also this other one later. But at least I also try to, towards the end of my lectures, I also try to discuss something which is maybe in between 1 and 2, which is a relation of what we do with the geometric, with sense theory or geometric sense theory, as was discussed earlier today by Lurie. So this I will at least try to do. And so regarding 1, to be a bit more specific, so let me first recall that p-adic Hodge theory is about comparing different p-adic cohomology series that we have for p-adic spaces. And for p-adic formal schemes, we now have a very good understanding of the situation because of the work of Bhatt Scholze and then later Bhatt, Lurie, and Drinfeld. And in this context, what we have is we have some kind of universal p-adic cohomology theory, which is called prismatic cohomology. And somehow it knows about all other p-adic cohomology theories that we like, and it also tells us how to compare them. And you can do even better than that in the same way that you can geometrize de Rham cohomology, say, by using the de Rham space or de Rham stack of Simpson. As was realized by Bhatt, Lurie, and Drinfeld, you can also do something similar for prismatic cohomology and construct some stacks called the prismatization of a p-adic formal scheme, or even some refinements of them. And so really the goal regarding 1, our goal was to get similar definitions and constructions when you replace p-adic formal schemes by rigid analytic spaces. And so if you try to do that, the geometry that you use is a bit different. It's not modeled on p-nilpotent or p-complete rings, but rather on the rings that you encounter when you do rigid analytic geometry. So I want to start a bit informally by just maybe recalling a bit like some maybe general stuff about rigid geometry and perfect grid spaces. And then I will try to explain why this geometric framework is somehow not good enough for the kind of constructions that we want to achieve, and why we needed to use a more refined setup. So that's the goal for today. So this more refined setup is, so that's the title for today, is a series of Gelfand stacks. So if I do well with time, that will be more or less the first half for today. But then I also want to, like in this geometric setup, I want to define the construction of the theory of the Rham stacks as somehow preliminary for the discussion of prismatization, which will come in the next talks. And then I want to apologize if you were there already for my lecture in September or October. I will basically repeat the same lecture today. It was actually the same room. Maybe I even have the same shirt. I don't know. But yeah, I promise that at least from the next lecture on, it will be some new stuff. But yeah, to set the stage, I need someone to discuss again this material. Okay, so maybe part 1 will be beyond perfectoid geometry. Okay, and so to start very basic, let me just first say that, okay, rigid analytic geometry is a p-adic analog of complex geometry. And of course, it took more time to somewhat set the theory off the ground because somehow the p-adic topology is totally disconnected, but so it's maybe less intuitive, but thanks to the work of Tate, Berkovich, and Huber, we now have really a theory of rigid analytic geometry which looks really parallel to complex geometry. But there is still maybe an important difference between the complex and the p-adic worlds, which is that if you take complex manifolds, they locally look very simple, because locally they just look like open disks, and so they are like locally contractible. But when you work in rigid analytic geometry, if you take a smooth rigid space, and then you maybe pick a point and look at small affinoid spaces, subspaces around this point, they still have a big étale fundamental group. And so they have still a non-trivial p-adic étale cohomology. So that's some kind of asymmetry, which really is one only because we take somehow for granted that so open disks are simple from the point of view of Betti or singular cohomology. And implicitly, maybe I'm assuming that Betti cohomology, like p-adic étale cohomology, is some kind of p-adic analog of Betti cohomology, which is a usual picture. I would like to argue maybe in the next lectures why this is maybe not the correct analogy from a certain point of view. But yeah, certainly that's a problem. In any case, whether this analogy is wrong or not, that's a problem you have to face, that the local structure of rigid analytic spaces from the point of view of p-adic étale cohomology is not simple. And so the way you deal with this is a very old idea, which I think goes back to Krasner, then Tate, maybe also Fontaine, Vinton-Berger. Is that things improve after extracting a lot of piece roots. And to use more technical but more precise terminology, the key statement here is that locally for the poétale topology, rigid spaces become perfectoid. So locally look like Banach rings, uniform Banach rings with a pseudo-uniformizer in which you can basically extract a lot of piece roots modulo when you go mod P. So if you allow yourself maybe not to localize for the usual like analytic topology, but for much finer topology where you allow like inverse limits of étale maps, then anything becomes, like any rigid space becomes perfectoid. And maybe the typical example is like if you take the Tate algebra in one variable over QP, and then you can, well, first you make the base field perfectoid, for example, by going to the cyclotomic extension, and then you also extract like piece roots of the, or maybe I want to take the rigid analytic torus, and then so that's a typical example of a perfectoid cover. It's even Galois in this case with Galois group, like some other product of a nice simple rigid space over structure. And of course, when you look at this example, it looks like you have replaced this nice Noetherian Tate algebra by some like complicated ring, a non-Noetherian ring. But the way in which perfectoid rings are simpler than like the rings you have to deal with in rigid geometry is because they can be tilted to characteristic P. And when you go to characteristic P, the condition of being perfectoid just becomes the condition of being perfect. And this allows you, that Frobenius is an isomorphism, it allows you to, typically you have some kind of vanishing of by theta cyclicity, you have some vanishing of cohomology up to some power of a pseudo-uniformizer. But using that Frobenius is an isomorphism, you can improve this to some almost vanishing. So like cohomology will, in higher degree, will be killed by any power, fractional power of the pseudo-uniformizer. And then when you invert P again, you get some vanishing on the nose for cohomology. So perfectoid rings are big, but they are very acyclic. You have a lot of vanishing of cohomology for them. And one typical way you can try to use this is on the poetal side, you have you have some Artin-Schreier sequence. You can resolve a constant shift Fp in terms of you have the structure shift. You take the power bounded element, and then you go mode P. And this is Frobenius minus identity, and this gives you a way to compute Fp et al. Cohomology in terms of this kind of cohomology. But say, for example, you want to prove, in the proper smooth case, you want to prove finiteness property for Fp cohomology. You could try to then, by this, you could try to analyze instead this kind of cohomology. And in the complex case, Carter and Serre have a nice argument for proving finiteness of coherent cohomology of a compact Kähler manifold by choosing covered by time spaces, which are like two finite covers, one being strictly embedded in the other. And then you just compare the Čech cohomology of both, and they both compute the coherent cohomology, but you observe that the restriction map is compact. Then some kind of functional analysis input will force the cohomology to be finite dimensional. If you want to do similar argument in this setup, then you need some kind of topology for which locally things become acyclic, like a replacement for time spaces, but for this kind of sheaf. So, and that's exactly what affinoid perfectoid spaces do for you. Okay, so that kind of application you find in the work of Faltings or in the work of Scholze. Right, and so if you push this idea further, then you end up with the notion of a V-stack or an arc stack. So maybe in the work of Scholze, typically it's this notion of a poetal or V topology that is mostly used. But for technical reasons that will show up later, I will prefer to work not in the setting of adic spaces, but rather of Berkovich spaces. And so this means I will work with this notion of arc stack instead of the maybe more familiar notion of, well, depending on your background, more familiar notion of a V stack. So you define the category of arc stacks. That will be my notation. Be the category of sheaves, or strictly speaking, it's really hypersheaves. So of anima on perf, which is my notation for a category of perfectoid spaces in characteristic P. Endowed with the arc topology. And here arc topology is a very fine topology, so a morphism A to B of perfectoid rings defines an arc cover if, when you look at the Berkovich spectrum, the associated map is surjective. And so, typical example, if you have X a rigid space, then you can naturally associate to it a certain arc stack, which I will denote X, call the diamond of X. Well, it's even an arc sheaf, which sends A, a perfectoid ring in characteristic P. So here, okay, maybe I even want to restrict to affinoid perfectoid spaces. That's good enough to define this category. By sending this to some untilt, A sharp of A, plus a map from plus on so some untilt A sharp plus some A sharp valued point of X. And so, yeah, if you care about things like étale cohomology, p-adic étale cohomology, this arc stack as X diamond associated to X is a very good replacement of X. So that's really, if you push this idea of really localizing for the pro-étale or even arc topology so that everything becomes perfectoid, that's somehow really just implicitly the idea of replacing this rigid space by its incarnation as an arc stack. Yeah, and so you can do quite a lot with this idea. But this theory of arc stacks has some limitations, and I want to maybe list two of them to explain why we want somehow to go beyond this geometric setup. And this will be somehow going back to my two motivations. The first, maybe drawback, is related to point one. And so it's just the basic observation that there are no non-zero differential forms on perfectoid spaces. So in this example here, for example, if you look at the differential of T, like you see that when you pass to this, when you replace the state algebra by this perfectoid cover, it becomes like infinitely divisible by P, and so in the P completion it will die. So this means basically that theory of arc stacks is very good at capturing like topological properties of X. Like for example, it's tell you things about its p-adic étale cohomology, but it's not so good at telling you how this compares to de Rham or filtered de Rham cohomology, for example. And precisely because we want to understand this kind of comparison results, it would be nice to have a class of rings which somehow sees also this kind of differential properties.
You mean there are no nonce? There are non-zero differential forms. No.
Yeah, sorry. Thanks. So that's one issue. And maybe another one is, so there is a functor from category of topological spaces to arc stacks, which sends a topological space T to an arc stack, which is usually denoted by T underline, which is, so again, it's sending a perfectoid space S to just like continuous functions from like its underlying topological space to T. And so in particular, if G is a topological group, let's say even like say a p-adic Lie group, well, then you can in particular realize it as an arc stack, and you can look at the classifying stack of G underline, where point just means the final object of this topos, so it's just like something which is sometimes also denoted SPA-D FP, or maybe FP bar. And you would, like, this is like sheaves on this stack would be some category of representations, but this only somehow remembers G as a topological group. But if G is a p-adic Lie group, there may be, as we saw earlier today in Lue's talk, there are like maybe other categories with p-adic coefficients, like various class of categories of representations we may want to work with, like continuous representations, smooth representations, locally analytic representations. And maybe we don't want to just have one geometric object and then change the sheaf theory to get these various categories of representations. It would maybe not even be clear how to do that. Rather, we would like that this p-adic Lie group is incarnated as a group object in some geometric category in different ways, depending on which kind of representations we want to work with. And well, this is not something you can really do in the world of arc stacks. And that's not really, I want to stress that that's not really due to the fact that I restrict myself to perfectoid space, perfectoid rings instead of more general Tate-Huber rings. Like in the theory of Berkovich or in the theory of Huber, when you take, say, in the world of Huber, for example, when you take a Tate-Huber ring, a Huber ring, and you look at its associated adic space, it only depends on the completion. So typically, you can't really distinguish between like rings of locally analytic functions or rings of continuous functions. So you need a geometric framework where you can distinguish between these different rings. Okay, and so that's what we'll try to. I want to explain now how to do that. So maybe there first, before I move to this, are there any questions about that? Okay. Okay, and so just to come back one more time to this. So here, what was the idea? We have a class of rings which we like, the class of perpetuate rings on which we would like to model our geometry, and then we just undo this category of rings with a certain topology and look at sheaves or stacks for this topology. Right? So it's very analogous to maybe say usual algebraic geometry. You just have the category of affine schemes, which is just the opposite of the category of commutative rings. And then you pick any Grothendieck topology you like Zaleski et al., FPPF, and so on. And you look at sheaves or stacks for this topology on affine schemes. So that's a bit similar idea that we have here with a very different class of rings and a different kind of topology. And so we want to enlarge our category of test rings so that we can typically distinguish between these different incarnations of G. So there is a very general way of, and note that the rings we will be working with, they will have some natural topology on them. So there is a very general way of dealing with this kind of questions, which is analytic geometry in the sense of Clausen and Scholze. And so maybe I first want to briefly recall, very briefly recall how this goes. So the idea will be a bit the same. We first define a certain class of topological rings we will be working with, pick a topology on this category, and then look at like sheaves for this topology. Right. So for the first step, the key definition is the notion of an analytic ring, which is a correct notion of a like topological ring one has to work with. So it's not just a ring, a topological ring. It's actually a pair, a triangle dA. So where a triangle is a condensed ring, well, and everything I'm doing will be at least at some point always like derived. So it's really animated condensed ring, but yeah. If you don't know, you can, for many things I will say, you can also just assume that it's a usual, like it's static, not derived, and if you don't know too much about condensed mathematics, you can also maybe just in first approximation imagine that this just means topological. And then dA will be a certain full subcategory of just the category of all a derived category of like condensed A triangle modules, which has certain properties. So, and I won't list all of them, maybe just want to point out two important properties. So it's stable by arbitrary limits and co-limits. And it also contains a triangle itself. And yeah, so there are some other properties which I don't want to list. And here, again, if you think to this as like the category of all topological modules over this topological ring, maybe a good approximation to this is you should think that there is a certain, like you specify a certain notion of being complete. So it's something like a complete A modules. Except that, okay, here you are basically, for example, requiring that the ring itself is complete. What's maybe slightly counterintuitive with this analogy is like it's stable under all columns, for example, which maybe you would not expect with the usual notion of a complete module. Okay, and so maybe then as a notation, then you just define exactly like affine schemes. You could define as just you take the category of analytic rings. So you have a natural notion of a morphism of analytic rings, and you take just the opposite category. So you just declare that affine analytic stacks are just like opposite category of analytic rings. And the notation one uses is it's purely psychological. It's just notation to such an analytic ring A. The corresponding affine analytic stack is denoted and spec A. So that's almost step one of the construction. And then you define the category of analytic stacks as the category of sheaves of like anima for a certain topology called the Schrick topology on so it's sheaves on anima on the category of affine analytic stacks for the Schrick topology, and I don't want to define the Schrick topology. Again, in terms of intuition, you can just think that it's something like the finest topology for which you have descent of this category dA of complete A modules. But not just descent of this category, but also like the 6 operations you can define. So in particular, as a consequence of the choice, and I will give later an example where this can be made a bit more concrete, but an important consequence of this is precisely because you choose its topology in this way, for any analytic stacks X, you have a certain infinity category of what I will call a category of quasi-coherent shifts on X in such a way that if X is affine, then this category of quasi-coherent shifts is precisely this category of complete A modules, which is part of your datum when you define what an analytic ring is. Okay, so it's a very brief recollection on this general notion of analytic stack. And of course, to make this interesting, you have to supply examples of such. And I won't make an overview of all the nice examples one has. Maybe just list like 2 relevant examples. So first, this is this category of this analytic ring structure that you have on QP called the solid analytic ring structure. So what is this analytic ring? Well, it's just QP. I will just use the same notation for the ring, topological ring QP and the corresponding condensed ring. So it's just QP endowed with its natural topology. So p-adic topology. And then you have a certain category, which in this case is just a derived category of a certain abelian category called solid QP. This is a category which has, it's an abelian category which has one compact projective generator. Which is given by the product, countable product of copies of ZP, and then invert P. Okay, so it's an abelian category with one compact projective generator, so you can just, like, then it's just really the category of modules over the endomorphism ring of this object. There are other ways to define this category. Yeah, so that's an example of an analytic ring structure. And maybe I just want to stress here that, okay, like this contains, for example, this category contains like QP, like Banach spaces, but it also contains, like it's stable also under limits and colimits. And here I just want to stress that when you compute, like say, filtered colimits, it's really like uncompleted. Right? And the underlying ring, it's really just the uncompleted filtered colimit. So typically, something which is complete is just an arbitrary direct sum of copies of QP. This is also complete. Sorry, solid. And once you have one example, you can make many more examples by a general construction. So if A is a solid QP algebra, so it means that it's like a QP, like condensed QP algebra, which is like the underlying QP module is solid. Then you define an analytic ring structure on A called the induced analytic ring structure. By just taking, as a condensed ring, you just take A. And then this category of modules that you work with is just the category of all like condensed A modules. Sorry, my notation is not really compatible. Like, yeah, this is what I would have denoted before A triangle. And you just look at all condensed A modules which are solid, such that M is, while the forgetful map is solid as a QP module. And in fact, that's all I need for these lectures, because we will always just work with induced, in this sense, induced analytic ring structures. And as a remark, maybe if you have a morphism A to B of solid QP algebras endowed with like induced, so then you get a morphism of analytic rings when you endow them. So sorry, maybe I should say. Then the induced morphism of analytic ring is a Schrick cover if and only if the morphism A to B is this map A to B is descendable, meaning that A belongs basically to the smallest subcategory of the A, which is generated under limits, finite limits, and retracts by B. So it has some kind of finite resolution by B modules. So that's a notion that has been introduced by Akil in slightly different context, but which also makes sense in this setup. And yeah, so that's one example of simplification that you get by restricting to induced analytic ring structure. In terms of intuition, again, you may think to this assumption, this restriction, to a bit analogous to something I already said, that I will not work in the setting of Huber-adic spaces, but I will work in Berkovich setting. That's a bit analogous to this kind of restriction.
So you want to define the lower Schrick.
Say again?
Define the lower Schrick.
Yeah.
And is that something one can do purely with that? I mean, I thought one has to use that on, you want to define a lower Schrick functor. I thought one has to use the.
Well, you can still do it with, sorry, I'm not sure what the question, like, it's just that no morphism between affine analytic stacks would be proper. Right?
So lower Schrick will be lower star.
Lower Schrick would be lower star in this case. But yeah, that's fine. It's just, yeah. Yeah, it's, okay. Maybe I come back to this a bit later. Okay, and so still, so I want to do non-Archimedean, like p-adic geometry. So certainly I don't want to work with general analytic rings. I certainly want to restrict to the one which lives over QP solid. And even more, as I said, I want to reduce to just considering the one with induced analytic ring structure. But even then, this is still not restrictive enough because we really care about rigid geometry. And again, in this analogy with maybe Huber theory or Berkovich theory, in Huber theory, in the category of adic spaces, you not only have like rigid analytic spaces, but you also have, for example, schemes and formal schemes. And this is the kind of examples I want to discard. So I want to, like an example of a ring which is a solid QP algebra is something like the polynomial. Like the underlying QP module is just a direct sum of copy of QP, and that's certainly solid. And that's the kind of example that I don't want to work with, because like unspec of this would be something like the algebraic affine line. And we want to really be closer to rigid analytic geometry, where you would be considering something like the analytic affine line instead. So this means I want to impose some further restrictions on the category of solid QP algebras I will be working with. And that's some of the key definition that I want to give now. So to make sense of this definition, I have to do it in several steps. So let me fix a solid QP algebra A. So the first observation is that if you have a, say, a non-negative real or rational number, you can make sense of, one can define a certain condensed subset or subanima, because we work, everything is implicitly derived, denoted A less or equal to R inside A, which intuitively speaking will be the subsets of subanima of elements of norm less or equal to R. And I won't give a proper definition of this, just some intuition, maybe what happens on underlying ring. So for like any condensed ring, so it's a sheaf of rings on light profile sets. And in particular, I can just evaluate on the point. And then I get a honest ring. And this is what I call the underlying ring. So what does that look like in this example? What is this subset? So an element of F of the underlying ring of A, so A evaluated on the point, or it's just the same as a morphism from, maybe I still denote it by F, from polynomial algebra in one variable to A. And I want to say that it is of norm less or equal to R if this map extends, if F extends to a map from, what's my notation? From, I will denote it like this. Well, no, the notation is maybe not optimal. I change the position of this symbol, so no, it's not an exponent, it's no subscript. And what is this? It's just the algebra of over-convergent rigid analytic functions on the disk of, on the affinoid disk of radius R. Sorry, that's maybe a bit small. Okay, so just to repeat, I look at all, like I have this affinoid disk of radius R in one variable, and I look at this, just not functions on it, but over-convergent functions. And I want, I think it's a bit rather natural to imagine that if these elements have norm less than R, basically I can form like arbitrary, like if I evaluate, if T goes to my element F, then it makes sense that this kind of sum will converge in A being solid. And okay, this is like really a property because it's this QP, this algebra over the polynomial algebra is idempotent. So that's really a condition. And in general, you do something analogous. So you are not just trying to define some anima, but some condensed anima. So you have to do it for arbitrary light profile sets. So to really define So that would just define the underlying set or anima. And to really define this in general, you have to define something which is denoted QP. What's our notation? QP and less or equal to R, some idempotent algebra of algebra of over-convergent functions on the S-dimensional disk, whatever that means. I mean, if S is a point, or maybe just a finite set, that would really be some kind of over-convergent Tate algebra, infinitely many variables. In general, it's a certain idempotent algebra over the free solid QP algebra over S.
Can I ask?
Okay.
Just why do you have the overconvergent condition?
I think it's just a little bit better behaved if you use this overconvergent version rather than just the usual, like the affinoid disk. Like this, for example, would be like countably presented, but not the affinoid version. And also, the idea is that this is like really somehow defining some kind of map from unspec of A to the interval 0 infinity, like more precisely the basis stack of this interval. And there, if you look at some interval 0R, it's really the limit of the interval of limit of the interval 0S when S is bigger than R. Right? So whatever, if you want to have such a map, then you are forced somehow to look at the overconvergent Tate algebra, not the Tate algebra. Okay, so maybe quick, just an observation at this point is that this is a subring. When I take R to be 1, I get a subring of A. And you always have a natural map. You say that so now you say that A is bounded if the natural map from A less or equal to 1 with P inverted to A is an isomorphism. And the terminology is justified by the intuition that, you are saying that any element of A is bounded. Any function on unspec A is bounded, because basically you are asking that when you have such a map, it will extend to the overconvergent Tate algebra of some radius smaller than infinity.
So if you take an element bounded by R and you multiply by the right power of P, do you always kind of shift it to be less equal to 1?
Yeah, that's correct, yes. And finally, you say that A is Gelfand if not only A, so first of all, A is bounded, but also you want to require that the uniform completion of A, which I will denote by this symbol, AU, which is defined to be, so you take this, what I will call power-bounded elements of A, you take the p-adic completion of this, and then you invert P. And this you require to be a Banach algebra. So equivalently, when you look at this power-bounded element and you reduce mode P, a priori, instead of being an arbitrary solid FP algebra, it's discrete.
What?
Discrete, like just has a discrete topology. Okay, so I now give some examples and non-examples, but maybe first one more remark. But if A is bounded, the reason for why this condition is useful is because this you can also plug in R being 0. That's something that is also sometimes denoted nil dagger of, this is a dagger, nil dagger A, and called the dagger nil radical. Then this is an ideal. Of A. So this you have like this subset or subanima you have to think to as like the, so it's by definition the elements which have norm 0. So it's like elements which are overconvergently close to 0, like infinitely, like they live in the power bounded part, but they are also, whenever you divide them by the power of p, they still remain power bounded. And so in particular, if A is bounded, you can make sense of the quotient of A by its diagonal radical. And we will make use of this later today. So just know some quick examples. So, well, Banach QP algebras are Gelfand. But also, this category is stable under colimits, but also colimits of such. So all the rings that you see in rigid analytic geometry, so Tate algebra, but also overconvergent Tate algebra, which are like filtered colimits of Banach QP algebra, they are examples of Gelfand rings. Yes?
Is it correct that 7 and 8, A less than or equal to 1 can be used with filter colimits?
Yes, that's I think correct. Yes.
Actually, is that because of this? Because it's an overconvergent functions, or that would it be different if you?
Wait, no. Maybe you have to be a bit careful about that. I'm not sure this is actually true. Maybe if you take strictly less than R for any value of R, then this would be, I think, fine. But yeah, no, I don't think that's true. That like if you take just this, for example, this when I don't know for any value, like say R equals 1, you take this to be your A. You take the identity map, and then it won't really factor through. But if you replace this less or equal by some kind of like open condition, then I think it becomes true.
So that being bounded is closed under filter colimits, is that right?
Yes, even like arbitrary colimits, yeah. So yeah, I forgot to say category of analytic rings as like small colimits. And this category of bounded or Gelfand rings is also stable under these colimits. But again, these colimits, filtered colimits are really, I stress it again, are really uncompleted. So non-examples.
Somehow, then when you check the Gelfand condition, you kind of have this colimit of Banach thing. I mean, somehow the things a priori not Banach, but individually when they complete their Banach. And then when you kind of take a colimit and then you complete there, it's like you complete them individually, take some kind of colimit and complete again.
That's correct, yes, exactly. Yeah. By complete meaning uniform, this kind of uniform completion. Yeah.
So a toy model will be like taking a direct sum of copies of QP, and then somehow p-adically completing that to get something like that.
Mm-hmm. Yeah, exactly. Yeah, so non-examples. So QPT is not Gelfand because it's not even bounded. So the idea is that this element T is not a bounded function. Just if you stare at the definition, you see that like you just take the identity map from QPT to QPT, you cannot extend it to some overconvergent Tate algebra. So T is not bounded. But there are also examples which are bounded but not Gelfand, like typically something like this. So power series ring over ZP and with P inverted is not Gelfand. It is bounded, but the power bounded element will be given by just this power series ring. But it's not Gelfand because, for example, if you go mod P, then if, like power bounded elements are given by this, then you reduce mod P, you get a power series algebra over Fp, which has with its natural p-adic topology, and that's not discrete. All right. Okay. And so now we can, that's the class of rings we want to work with. And then we can just redo this definition 2 here and define Gelfand stacks. The category of Gelfand stacks as the category of sheaves on, maybe I should have introduced this notation. So Gelfand, Gelf ring will be the category of Gelfand rings. And then I just look at this category, I take the opposite category. So sheaves for the, because I always work with the induced analytic ring structure, I can just say for the descendable topology. Okay, so the relation between this so this is if you want a variant of the category of analytic stacks over QP solid. Like there is a natural like co-limit preserving functor from Gelfand stacks to arc stacks. So by the way, as notation, if again I need some notation, so if A is Gelfand, like I will denote by G spec A instead of An spec A, like the functor which is co-represented by A. So that's the corresponding affine Gelfand stack associated to A. And so I was saying there is a natural functor from co-limit preserving functor from Gelfand stacks to all analytic stacks which sends G spec A to An spec A. But I don't know if it's probably not fully faithful in general. But it's also not maybe so important. We'll just stick to Gelfand stacks from now on.
In general,
Mm-hmm.
so that everything is over QP. Is there an analog if you replace QP by something else?
Yes, I think as long as you have a pseudo-uniformizer, basically, then you can make sense of this. So I think more precisely, I think you can make sense of all these constructions over the stack of norms. I think that may be discussed at the end of this lecture by Maximilian. Yeah. So for example, you can work over something like ZP double power series pi for some pi.
Sorry, stupid question, but so property of being Gelfand is only on underlying condensed ring, right? Property of being Gelfand.
Say that again.
The property of being Gelfand is only something defined on just the underlying condensed ring.
Yeah.
You're saying that Gelfand. Okay, so. I mean, it's implicit, of course, what you mentioned earlier, but it's
sorry, maybe I should have made this more clear. This Gelfand rings is a certain subcategory of all solid QP algebras, and then to see them as analytic rings, I always endow them with the induced analytic ring structure. And yeah, the condition of being Gelfand also only depends on the pi 0. So I was saying that there is a functor from Gelfand stacks to analytic stacks, which sends G spec A to An spec A, and it has a right adjoint. So I will never use that, but I just want to maybe point out what this right adjoint does in these two examples. So we saw examples of solid QP algebras which are not Gelfand. So what happens when I apply this like Gelfandification functor to them? So for example, if I take An spec of QPT, so that's really the analytic stack version of the algebraic affine line, and I take its Gelfandification. I get the analytic affine line over QP, which is a non-affine analytic Gelfand stack. So that's the Gelfand stack version. So it's really a co-limit over a union over all radius of like G stack of like affinoid disks.
Why are they called Gelfand stacks?
Yeah, so for Gelfand rings, you have a notion of a associated Berkovich spectrum, just basically by taking the Berkovich spectrum of the uniform completion. And I think at some point we saw that, I think we made a mistake at some point and thought we can make sense of this Berkovich spectrum construction for like all arbitrary bounded rings, and then the property of being Gelfand would have been equivalent to saying that a certain kind of Gelfand transform you get is like well defined as a map of condensed sets. But so that's where the terminology is coming from. I think it was from a discussion with Dustin Clausen, but yeah, then we realized that there was a mistake in this construction. So then I don't know, we kept this terminology, but with no good motivation. All right, so that's one example. So yeah, and maybe just for this other example, if I take n spec of, and this, and again I take its associated Gelfand stack, this will be just the open unit disk. So that's my notation for the open unit disk. So just to give two examples of this. Okay. Of course, for other purposes, it's good to have like this general flexibility given by the theory of analytic stacks that you can also make sense of this kind of analytic stacks. And you want maybe to, for some problems, you may want to distinguish this from this open unit disk, but at least for what we want to do, that's good enough. And other remark is that this category of Gelfand stacks, it contains fully faithfully the category of dagger or overconvergent rigid spaces in the sense of grosse Klone. In fact, even better than this. So this itself sits inside a very general version of like a derived notion of Berkovich spaces. And this also sits fully faithfully inside this category.
So what you said earlier, are you saying that if you take the, so up here there's two definitions, the analytic spectrum of ZP double brackets T and vert P is a Gelfand stack, and you're saying that's the same as the union of the closed disks of radius less than 1?
That's correct, yes. That's defined as as union of pieces. Yeah. I don't know, that's maybe not very standard. That's the notation I try to use. Yeah, so like this notion of derived Berkovich spaces is basically like a stack that you get by, so it's just something that you take like G spec of some arbitrary Gelfand ring, and then you glue such for the analytic topology. So you can define some version of the analytic topology where you just glue along rational localizations, which are basically pullback from the Betti stack of the Berkovich spectrum. And so there you get this general notion of a Berkovich space. And the reason I look at like overconvergent rigid spaces and usual rigid spaces is again because of this kind of restriction to induced analytic ring structure. So the fact that I work in the Berkovich rather than Huber setting. But so, for example, like you can look at partially proper rigid spaces. These are examples of such. Okay, so this also shows that this category of geometric objects that I have defined is like contains maybe the main examples we care about, for which we want to define some version of prismatic homology. And so maybe I will make a small 5-minute break, but maybe let me first end with, before the break, state a proposition. So it's a key property of Gelfand rings. So it's the following statement. So let A be a Gelfand ring. And then there exists a descendable cover A to B, with B is what we call a nil perpetuate ring. And so a nil perpetuate ring is a Gelfand ring. So B is Gelfand. And it has the property that B, when you model this dagger nil radical of B, then you want this to be perfectoid. When I say perfectoid, I always mean like Tate perfectoid. And so in this case, it also happens, it naturally maps to the uniform completion. This will also be the same as the uniform completion. So
that's not always true for Gelfand.
This property, you mean? No, that's not always true. But that will be, if I require that this like dagger reduction is perfectoid, then it implies this. In general, you just have an injective map. It may not be surjective. Right, okay, so that's just geometrically, this corresponds to some kind of over-convergent thickenings of perfectoid, affinoid perfectoid spaces. And you can do even better. You can even assume that B, that this dagger reduction is what is called strictly totally disconnected. So it's an even stronger condition. So it's not only just perfectoid, but basically it means that, so maybe let me introduce a notation for this kind of quotient. That's what I will call the dagger reduction and denote by B bar. So it means that the Berkovich spectrum of B bar is profinite, and residue fields are perfectoid algebraically closed. So it's just a bunch of profinite bunch of Berkovich spectra of perfectoid algebraically closed field. So here I'm a bit cheating. I mean, I've been cheating already several times in all these. Let me maybe point out that the definition of analytic stacks or Gelfand stacks that I was giving was a lie. I mean, the correct condition is a bit stronger than being just a sheaf. And here I'm also a bit cheating. To make this true, you have to impose some kind of countability and fine dimensionality assumption on the Gelfand rings you work with. And they will be implicit in everything I do from now on. And so, as examples, so maybe first, this subcategory of nil perfectoid rings is not stable under colimits, but it's stable under push-outs or finite colimits. And in particular, it's really like you could have defined Gelfand stacks just as stacks on this category of nil perfectoid rings instead. And if you think about it this way, you see that it's really close to the category of arc stacks I started with, except that I allow myself to replace like affinoid perfectoid spaces by over-convergent thickenings of such. So it's just some of the minimal choice I can make for geometric theory which is close to the theory of arc stacks, but where I can also speak about something like the dagger nil radical in a non-trivial way. And so just some examples of such. So of course, if you are perfectoid, so perfectoid rings are nil perfectoids. But less trivial examples are also if you take something I will denote by CPT. So if A is CPT dagger, so that's by definition colimit over all positive real numbers of, natural numbers of Tate algebra like this. So it's like really the over-convergent functions around 0 in A1. So that's also nil perfectoid. And in fact, the ideal generated by T is exactly the diagonal radical. You see that in this colimit, you made T of norm 0. You made it divisible by arbitrary powers of T. So in this case, A bar is CP, which is a perfectoid field. And more, also a more interesting class of examples is if you have any Banach QP algebra, and B is a quotient, then B is nil perfect. Sorry, is a perfectoid. QP algebra, and you take any quotient of A, then B is also nil perfect. And in this case, its uniform completion will be given by or its dagger reduction will be given by the generic fiber of the perfectoidization, in the sense of the perfectoidization of the power bounded part of A, in the sense of sorry, what do I want to write? So this will be something else. I hope I get that right. So you see that you can, that example also suggests that you can think of nil perfectoid rings as a bit analogous in this context to semi-perfectoid rings in integral p-adic theory. Analogously, like semi-perfectoid rings form a basis of, say, the quasi-syntomic topology. And there as well, like we have this descendable topology, and we can we have this nice basis of nil perfectoid rings. Okay, so I don't know, maybe it's a good time for a 5 minutes break. I don't know if there are questions. Maybe. So let me, before moving to part 2, I just wanted to add one more general remark about Gelfand stacks, which is that it's actually important for later. That for Gelfand stack, there is a well-behaved category of perfect complexes on X, which is a subcategory of like quasi-coherent sheaves on X, satisfying descent for the topology. For the Schrick or descendable topology, which. Or maybe a bit more precisely, what I'm saying here is that, you can even bound the amplitude. So for any integral interval AB, you have some the functor which sends a Gelfand ring A to perfect complexes on like just the underlying ring. And the claim I'm making is that this defines a sheaf for the descendable topology. And so then, in particular, you have like a well-defined notion of a category of perfect complexes, even with bounded amplitude for any Gelfand stack. And the key input to this is the fact that Gelfand rings are Fredholm. Terminology which has been introduced by Clausen and Scholze. Which basically means that all dualizable objects are just perfect modules. And the reason like why this enters is basically that, okay, like a priori, just on these Gelfand rings, it would not be clear that if you take such an A and you look at G-spec A, and then you take an arbitrary Schrick or descendable covers by other affine Gelfand stacks, it would not be so clear that something which is locally for this cover a perfect module is really a perfect module on A itself. But what you at least know is that it will be dualizable because this is a local condition, and then this property of being Fredholm is exactly telling you that this will be automatically a perfect complex. So we will use this fact several times later. Okay, and so now what I want to do is to discuss, to somehow illustrate what this formalism is good for. I want to discuss the theory of the Ram stacks. And I should also maybe have said that everything I'm discussing, actually I realized, I should have said it at the very beginning. What I'm discussing today is also joint with Bosco. And it's actually written down. So everything I have discussed so far is in a joint paper with Anschütz, Bosco, Rodriguez, Camargo, and Scholze, which is on archive. But okay, that won't be the case for what I'm discussing in the next lectures. But in the paper of Maximilian on analytic syntomification, there is a very nice discussion of, or summary of the theory of analytic prismatizations that you can also look at. And hopefully the paper will be available soon. But, okay, so back to the Ram stack. So maybe I want to start with a toy model for what we will be doing. So it's an example in characteristic P. So maybe I want to write, I don't know, stack. FP is a category of stacks on FP algebras. Let's say, I don't know, for example, for the descendable topology. And then maybe I denote by stack FP perf. The same category, but now I only look at perfect FP algebras, so on which Frobenius is an isomorphism. And again, for the descendable topology. And now you have a restriction functor or maybe I could also call it perfection, which just, okay, you have a functor on all FP algebras, you just restrict to like perfect FP algebras. And this has a left and a right adjoint. So the left adjoint is basically just a functor which sends, if you have a R, a perfect FP algebra, or the functor co-represented by R, you just send it to set R. And the right adjoint is maybe more interesting because it's a version of the de Ram stack. And more precisely, so the de Ram stack will be, like, I say a version because a priori the de Ram stack is something like the functor which sends R to some FP algebra to so the de Ram stack of some scheme in characteristic P. You would like to define it as a functor which sends R to x of the reduction of R, the quotient by the nil radical. But then that's a priori maybe only a pre-sheaf. And here we work with a descendable topology, so you take the sheafification of this for the descendable topology. But a basis of the descendable topology is like formed by perfect FP algebras, and semi-perfect FP algebras. And for semi-perfect rings, the reduction is the same as the perfection. So R is semi-perfect. And then that's just the same as the colimit perfection of R. And on semi-perfect FP algebras, this R goes to XR perf is already a sheaf.
So the fact that you had these adjoints given by these formulas, at the level of pre-sheaves, is it correct that at the level of pre-sheaves this would be true if you said lower perf and upper perf on both sides, that pre-sheaves on perfect rings, you're from with adjoints, and they're given by precomposition with lower perf and upper perf?
Yes, I think so, yes. Right, so that's, if you want, the reason I'm explaining this is because it shows that, so it's maybe not quite the de Ram stack you would like to consider in characteristic P, there are no divided powers and so on. But if you look at this version, so you just take usual reduction and you shift-ify for something like the descendable topology, then basically what you get is a right adjoint to this perfection functor. And so this shows that, yeah, you can think to the Ram stack functor as being adjoint to perfection. And so that's exactly what we will mimic in the setting of Gelfand stacks. We will define the Ram stack functor as right adjoint to some kind of perfectoidization functor. So what is so analog for Gelfand stacks? I never managed to write this. So you have again a restriction functor from category of Gelfand stacks to the category of arc stacks over QP. So over the arc stack of QP, which is again basically just restriction to from arbitrary Gelfand rings to perfectoid rings over QP. And this is what I will call the perfectoidization functor, or sometimes also maybe diamond functor. Yeah, so I will denote it with a diamond. So x goes to x diamond. And in fact, this functor, like, it's co-limit preserving, and it sends if I have something like G spec R. Where A is a Gelfand ring. It sends it to the arc stack of A. So the functor co-represented by A on perfectoid rings. So that's a notation, the arc stack notation for what you would maybe call the I don't know, maybe something like p-adic of A. If you use V stacks, that's maybe what you would, the notation you would use. So that's a notation produced by Scholze. Yeah, so that's what this functor does. Oops. And again, this functor has a left and a right adjoint. So the left adjoint is, so it will be a functor, so from arc stacks to Gelfand stacks, which I will denote x goes to x hat. So it's a left adjoint. So again, it preserves co-limits, and it sends, if you have R, which is a perfectoid QP, sorry, it's arc stacks over QP, it's a perfectoid QP algebra. Then you send M arc of R to G spec of R. So that's a way to realize, if you like, arc stacks inside Gelfand stacks. So the reason for this notation is that when you look at the coherent cohomology of this stack, it's basically so x is an arc stack over QP. So because it's an arc stack over QP, you have a structure shift in characteristic 0 O hat, and that's basically what it's computing. That's more or less from the definition. So in general, you write your arc stack as a co-limit of affine, affinoid perfectoids, and then you just, for them, you just map this to spec R. That's a useful construction, which we will also use later. But for today, I maybe mostly care about the right adjoint. And that's now like my definition of what the Ram stack functor is. Yeah, and so so if x is, one more piece of notation is that if x is Gelfand, a Gelfand stack, then I will slightly abuse notation, and I will also use the notation x to Ram. So strictly speaking, will not make sense because I need to input on arc stack. But that will be defined to be like, first I apply this perfectualization functor, and then I take the corresponding arc stack. And if A is a nil perfectoid ring, then and X is a Gelfand stack, then I have a functor of points description for what X the RAM of A is. And this is the same as X of the uniform or dagger reduction. Okay, so that's very analogous to the formula for the usual de RAM stack, except that I have replaced the usual reduction by this dagger reduction. So I model the dagger in radical. Yeah.
So I guess maybe in some talks in the last few years, there was some informal picture where in this analytic world, sort of the RAM stack construction should be quotienting out by the groupoid, which is kind of the overconvergent thickening of the diagonal.
Right.
Is that happening philosophically?
Yeah, I will state a result where this. Yeah, you're right. If you have in some class of examples, this is really just this kind of quotient. So I will write it later. Yeah.
Just in this FP picture, if X was A1, this is not what I would typically think of as the de RAM stack. This would be like GA mod GA hat.
Yeah, so that, no divided powers. So it's that's why I said a version of the de RAM stack.
So it's more like differential operators with like divided powers, as opposed to crystalline differential operators.
Yes, exactly. But also, I think usually maybe people do not shiftify for such a fine, like, okay. So that's a formula that is valid on, like it's not true if I input an arbitrary Gelfand ring, but if I input some nil perfectoid ring, I have this formula, like without any need to like shiftify this. Yeah, so that's really a functor of points description of this de RAM stack functor on some nice basis of the strict topology. And that's useful that you don't have to perform any further shiftification. Okay, so now let me state a proposition, like a theorem, which is in particular an answer to Matt's question. So the first part of the statement is that, and maybe what's hidden in these claims that you have a left and right adjoint is statements of the following form that if you have a descendable cover of Gelfand rings and you pass to uniform completion, it induces an arc cover. That's actually a statement for which the Gelfand condition is useful. But conversely, also, if you have an arc cover of, say, for example, nil perfectoid rings, then this is also a descendable cover. So this is the kind of statement that you need to check these adjunctions. Okay. And they also explain a bit some of these restrictions that I put on my rings, like countability or fine dimensionality. So the first part of the theorem is that this functor commutes with limits and co-limits. And so in particular, it preserves epimorphisms. So the fact that it commutes with limits is just because it's defined as a right adjoint. But still it's interesting because note that limits in arc stacks are really like some kind of, again, cofilter limits would really be something like at the level of rings, there is some completion involved. But so typically if I look at something like, I don't know, like the perfectoid torus, which I write as an inverse limit of rigid tori, and I take the corresponding arc stack, and then I apply the RAM stack functor, it will be a limit of the RAM stacks of tori, which are nice rigid spaces, but this limit is not computed in Gelfand stacks. So it's really some kind of uncompleted limit. So that's this feature that the RAM stack is kind of decompleting things. But that's, in this definition, that's sort of built in the definition because I define it as a right adjoint. This is much less obvious, and in particular, this consequence, you should think to it as telling you that this functor x goes to x the RAM has very strong descent properties. If you have an arc cover, of arc stacks, then sorry, yeah. If you have an epimorphism of arc stacks, you get an epimorphism on the RAM stacks. So that gives you a way to access, computing examples. Mm-hmm.
So if you restrict to null perfectoids, then you have a formula for x around is quite nice, and at least at the level of pre-sheaf, that commutes with collimets. Is there an issue of sheafification and so forth?
Can you say that again?
I'm just saying that formula, if you have that at the level of null perfectoid, that commutes with collimets, right?
Collimets in X, you mean?
Yeah.
Yes.
But I don't know. There's some sheafification and so forth that one has to do for that.
Sorry, no, I don't think there is. Okay, so yeah, but I'm claiming, okay, maybe I'm claiming commutation with collimets in arc stacks, right? And here I was like for this formula to hold, I was. Sorry, I'm saying something stupid now. Yeah, I don't think there was any need for this. Wait, maybe it was.
You're going from Gelfand to.
Well, you said epimorphism, and maybe an epimorphism is it an issue of starting with like an arc cover and sort of lifting that to a tree cover?
That won't necessarily be a shake cover, right?
Well, I think this is precisely the issue, right? I mean, the key thing that you have to prove is that if x to y is a surjection of arc stacks, then x to RAM to y to RAM is a surjection of Gelfand stacks.
And that involves lifting this kind of.
Yes. Okay, I'm still confused by your remark, no, but.
My remark was a level of pre-stacks, but maybe the issue is two different topologies.
Yeah, I think
the
issue is that you have different topologies.
Okay, yes, no, I get it, yeah. Sorry. Okay, so the second statement is the answer to Matt's question. So if X is a dagger rigid space, so e.g. a partially proper rigid space, or something like an over-convergent disk, then the RAM stack of X, which now I'm using this notation, I see this as a Gelfand stack, as I explained before. I have this fully faithful functor from dagger rigid spaces to Gelfand stacks. And now this is just the quotient of X by the over-convergent neighborhood of the diagonal. Yeah, I'm not sure how to denote this. So I have the diagonal embedding of X in X times X, and I just look at the over-convergent neighborhood of the diagonal. And in particular, okay, so this you see that this is maybe another more familiar description of the RAM stack as some kind of quotient. In general, you always have a natural map from X to X the RAM, just because you are applying like first some functor and then it's right adjoint. So then you do get a map like this. It's just not true that in general that this is an epimorphism, but under this assumption, you can prove that. And so it looks like the formula for the RAM stack of Simpson, except that observe that you have replaced the formal completion as an in scheme by this over-convergent completion. And this means that you are not really, when I said the RAM stacks, I should always maybe say analytic the RAM stacks, because really the category of sheaves on these stacks you have to think not as like algebraically modules, but as some kind of analytic modules. So in the case of the affine line, you could look at some algebraic Durham stack of the analytic affine line, and that would be somehow imposing no convergence condition in the cotangent direction. But here you are also somehow imposing some convergence conditions.
Parallel to the models with the infinity differential operators of infinite order in usual analytics.
I guess it's related. I just don't know very well what this D infinity means. Yeah, so maybe let me.
Infinity is something usual differential operator are cohomology. You take square, you take diagonal, and consider cohomology with support of functions exterior tensor product forms, something like top forms, and in algebraic geometry, and this is if you do it in analytic geometry.
Okay. Yeah, that sounds plausible. I think in this p-adic situation there is like a precise statement you can make that the category like maybe let's say this one, like here I did not even assume it's smooth, but for a smooth, let's say partially proper rigid space, then the category of quasi-coherent shifts on this stack should be the category of D-cap modules. Like Ardakov and Watsley have defined some series of p-adic D modules on rigid analytic varieties. And I think that's precisely what you get. I mean, maybe a condensed version of this. But one consequence is that, in particular, this will be computing the Durham cohomology of X, so, which somewhat justifies the name for this construction. And yeah, you also have a nice aspect of the theory of analytic stacks, in particular of the theory of Gelfand stacks, which also will be a motivation for the theory of analytic prismatization, is that if you have defined something as an analytic or Gelfand stack, you have a category of quasi-coherent shifts on it and 6 operations. So you have a full 6-functor formalism. So this you can use for the Durham stack, and say if you have a morphism which is smooth, say of relative dimension D, then if you look at the induced morphism on Durham stacks, then this is cohomologically smooth, meaning that upper Schrick and upper star functor are the same up to twist by some invertible object. And this invertible object is upper Schrick of 1, and it's called the dualizing sheaf. And this dualizing sheaf is just the structure sheaf on X Durham with a shift by 2 times the dimension.
Is it possible to say concretely what this F lower Schrick is doing? Say if you have a point.
Yes, I think for an open disk it would just be QP sitting in degree 2, cohomological degree 2.
Sorry, I mean the lower Schrick. The
lower Schrick, yes, I think that's.
I mean, of some D module.
Some RB. Sorry, I thought you were trying to just compute for the structure sheaf for the units.
Will it be some sort of compactly supported Durham complex?
Yeah, it's some kind of compactly supported Durham cohomology. I don't think I have a much better answer than this. Yeah, I also think, okay, I also have to say that somehow we did not really investigate. I made this claim that this is related to the theory of D-cap modules. This is not part of our paper. This is, I think, work in progress of Camargo, Rodriguez-Jacinto. But so the exact relation with like 6 functors on usual D module or like D-cap modules, this is not something I've thought about really. So. Okay, so let's give a few examples. So if X is the analytic affine line, then it's the Durham stack. That's just a particular case of point 2. I mean, this has a structure of a group, so you just get a description as a quotient of A1 analytic by something I will denote by GA dagger, and GA dagger is notation for like some kind of overconvergent disk around 0. So it's a spec of G spec of this Tate like this. So algebra of germs of regeneratic functions around 0 that I introduced before. I mean, I wrote it over CP, but you can also, of course, define it over QP. So it's just a quotient for the natural action of this by translation. Another interesting example is if you take the affinoid disk D, so that's just G spec of QP T, then X the RAM is given by, so in this case, in fact, the natural map from X to X the RAM is not surjective. So really the correct description of the RAM stack is you take the overconvergent disk of radius 1, and again, you model by the action of GA dagger by translation. So this is, by definition, G spec of this algebra of overconvergent functions of radius 1. And so this means that in this example, the cohomology of this stack will be computing like overconvergent de Rham cohomology instead of just a naive de Rham cohomology, which is in some sense good because this is the one which has better properties.
So just to clarify, so the de Rham stack sort of erases the difference between D and P over T. Is that right?
It's supposed to be a dagger. So
Dagger, sorry. Because one is the uniform completion of the other local friends.
Yeah, that's right. The uniform completion of this ring would just be this one. Yeah. Yeah. So the corresponding arc stack for both are the same, right? So after the associated, the perfectoidization only depends on the of like a Gelfand ring only depends on the uniform completion. Yeah. So if I could apply 0.2 to the overconvergent disk and get this description, but what I'm saying is because they have same uniform completion, they have the same de Rham stack. So in particular for this, you can think to this as some kind of compactified disk of radius 1, and the claim is that it's the RAM stack like computes its like overconvergent de Rham cohomology. Another example, if you take X to be just the arc stack associated to a topological space, notation I introduced before, then the de Rham stack of X is a construction called the Betti stack. So it's a construction due to Claus and Scholze, which is a way to realize topological spaces or even condensed anima as analytic stacks. And this also works in Gelfand stacks. So like quasi-coherent sheaves on this Betti stack are just the same as sheaves on the underlying topological space. Sorry, on the underlying topological space.
T underline and T underline Betti.
So T underline is an arc stack for me. Sorry, that's the notation. But maybe, okay, now I base chance to, I see it over QP. And now I take its Betti stack. So like the Betti stack is living over Z, so maybe implicitly I'm doing a base change to QP solid. Okay. And so I will use this to make some kind of, this one is not really an example, but maybe more a definition. If you have an algebraic, like a rigid analytic group over QP, so for example, the analytification of an algebraic group, then you know that the de Rham stack of G, okay, so it's something, it's like generalization of first example here, it's like a quotient of G by something I denote by G dagger, the overconvergent neighborhood of the unit section. And now you have a natural map. If you look at arc stacks, if you take the QP points, that's seen as a topological group. So G QP underline maps to the arc stack of G. And when you pass to the de Rham stacks, so okay, that's by definition what I call G de Rham. But now, by this example, this is just the Betti stack. So in this case, it's like locally profinite. So that's also something I could write as the smooth incarnation of GQP. So just something which, if G is compact, this would really be just like a spec of locally constant functions on GQP. So I get a map like this, which is an immersion, and so now you can define the locally analytic incarnation of GQP as a fiber product of GQP smooth with G. So I'm using this map here, and there's a natural map from G to G de Rham. And so intuitive, like geometrically, it's some kind of like you are looking at, by doing this fiber product, you are taking GQP sitting inside the rigid analytic group G, and you are doing like looking at the overconversion neighborhood of GQP inside G. So that one is, as I said, more definition than really an example. Okay, so I don't have much time left, so I wanted to discuss two more things. I want to discuss, okay, first thing I want to discuss, maybe I do it in the form of a remark. So we just defined a stack which somehow geometrizes rigid, the Rham cohomology of dagger rigid spaces. But on the Rham cohomology, we have the Hodge filtration. So it's, of course, natural to also try to geometrize this piece of structure. And, well, also from work of Simpson and more recently, Bhatt, Lurie, Drinfeld, and so on, we know how to do that. It's a construction called the filtered de Rham stack. And I wanted to do it in a way which is maybe not exactly the way it's usually done. Let me do it in a slightly overcomplicated way, because this allows me to introduce some useful notation for future talks. For this, I need a definition. So if I have an arbitrary Gelfand stack, I define what is called the cone construction, define Y cone. So it will be a stack over A1 mod GM. And from now on, when I write A1 and GM, it always means analytic A1, analytic GM. I just don't want to write over QP. As a functor, which sends, so if you have a map, a Gelfand stack Z with a map to A1 mod GM, it's the same as giving yourself a line bundle, so that's a map to BGM, and a section, like possibly 0. So sending, so in other words, some kind of generalized Cartier divisor on Z, sending Z Gelfand stack with a Cartier divisor D on Z. So I just write this as a notation, but beware that, as I just said, this is not really a Cartier divisor in the usual sense. Like you have a line bundle with a section which may not be injective. And you send this to Y evaluated on Z. Okay, so that's what we call the cone construction. And it has a funny geometry, so slightly strange. So if you base change to over A1 mod GM to GM mod GM, which is just a point, then this just becomes a point. That's basically because this is the locus where.
Y, did you mean Y or you mean Y cone?
Y cone, thanks for that. That's basically because this is a locus where this section is invertible. So this divisor will be just empty, and so you just get spa QP. But over if you now look at what happens over BGM, so over 0, the origin of A1. So now there is a natural map to Y, and if Y admits a cotangent complex, this will be just given by, now I have to write this correctly, this identifies with this base change to this base change of the cone construction with some truncation of the tangent complex. So if I wrote it correctly, you take truncation. So you take the tangent complex of y, just defined as linear dual of the cotangent complex, and you truncate here, and then you shift by 1. So, okay, maybe most importantly, if y is a smooth, say for example a smooth rigid space, this tells you that over this over BGM, what you get here. So maybe as notation I call this y Hodge. And the reason is that because of this, if y is a smooth rigid space, this will really just be the classifying stack of the tangent complex of y, which is just dual to cotangent. And I call this, we call this cone construction. I don't know if it's a standard terminology, because there is also a relative construction. So more generally, if you have like a map y to x, then you could define a relative cone construction by taking so you take the cone construction, it's functorial, and then you observe that there is always a map from x times a1 mod gm to x cone. Just because there is always a map from like d to z, so at the level of like evaluating, like taking the points, this gives a map from x to x cone, and of course you also have everything lives over a1 mod gm. So you can form this base change. And if I would be like in a situation where this would be, if y is a regular closed immersion, then this would be some kind of deformation to the normal cone. Like generically, this is no, for this relative construction, generically this is no x, so over gm mod gm. But if you look at the fiber over 0, no, you really get just the normal bundle of y over x. And sorry, here I forgot some kind of, there is also a twist. This twist means twist by the invertible. Like there is a universal line bundle on BGM, and I pull it back. And this gives me also, so there is some twist involved. Sorry, that's maybe a bit too quick, but I just want to get to the definition. So I define now the filter de Rham stack. So for this definition, it's no important that I start with a Gelfand stack and not with just the associated arc stack. And you define y de Rham plus, called the filter de Rham stack, as so you take the de Rham stack of y, the de Rham stack of a1 mod gm, and so as I said, there is a map from y times a1 mod gm to y cone. I take the induced map on the Rham stacks, and I just base change it to y cone. Okay, so that's certainly a complicated way of writing what this filter de Rham stack is doing, but maybe for time reason I leave as an exercise just as writing on nil perfectoid ring what this is doing, and see that this maybe on the maybe you need some small condition on the Gelfand stack and check that this if you know already what the filter de Rham stack is, that this will coincide with the usual definition. But how I want you to think about the right-hand side is some kind of relative de Rham stack. For this map, y times a1 mod gm mapping to y cone. If you know what the relative de Rham stack construction is, this is exactly this in this particular, for this particular map. And we will see later as in the analytic prismatization there is a similar behavior, except that the source here will be replaced by something more complicated. So that's the reason I wanted to present it in this way. Yeah, and so basically, the cohomology of this analytic de Rham stack is related to, as you would expect, to the Hodge filtered de Rham cohomology. Okay, and so that was maybe remark one. And to finish, another remark is about like what is called Yodo-Kato stacks. So there is something a bit surprising about this theory of analytic de Rham stacks. It is that it makes sense. Analytic de Rham stacks, by definition, make sense for any arc stack. If you think intuitively of what the de Rham stack is supposed to be, it's like supposed to be about D modules, which are defined in terms of differential operators. And because of what I said at the beginning, that there are no, like, I don't know, like in general, you would have imagined maybe that this is only reasonable when X is smooth, or something like this, and then you have to extend. But really, the fact that we work not with the algebraic de Rham stack, but with the analytic de Rham stack, makes it a very topological object, so to say. So in the complex case, you can also do a similar thing, and then by result of Clausen and Scholze, the analytic de Rham stack is just a Petit stack, which is maybe a case where you can really, like, make more precise this idea that this analytic de Rham stack is really a topological construction. And so this is nice because this gives us a lot of flexibility. Now we can make sense of the de Rham stack of very strange objects. So an example of this is if you have any arc stack, so not necessarily over QP, then you can define its Yodo-Kato stack. So you take X, so it lives over the arc stack of Fp, which is a final object. And then you just take this fiber product with arc stack of Qp. So now it's an arc stack over Qp. And now you can take its de Rham stack. And if you want this Yodo-Kato stack, I further, so there is a natural Frobenius on X, just because it's a functor on perfect weight spaces in characteristic P. And so I want to mod out by Frobenius on X and identity on the other factor. And then I take the de Rham stack. So that's something you can now make sense of. And as I will recall on Wednesday, this is basically something called the Fark-Fontaine curve of X, as a diamond. And so this is a de Rham stack of a relative Fark-Fontaine curve over X. So sheaves on this stack you imagine as some kind of analytic D modules on these relative Fark-Fontaine curves. And so maybe I don't want to say much more about it. So the idea is that why this notation? So if X is just the arc stack associated to a scheme in characteristic P, the cohomology of this stack is basically computing rigid cohomology. It's a work in progress of Drinfeld. If no, instead X is something like a rigid space, say a smooth rigid space, partially proper over QP, then what you are computing is this Yodo-Kato, like at least expectation for now is that this is computing some maybe over-convergent version of the Yodo-Kato cohomology of Coleman and Initial. So they have defined some Yodo-Kato cohomology for rigid spaces, which maybe smooth rigid spaces, which if you have a nice semi-stable model, it's just the usual Yodo-Kato cohomology of special fiber. But so they have a definition which works for arbitrary smooth rigid spaces, and the expectation is that this is a stack which geometrizes this Yodo-Kato cohomology. Right, and finally, you can combine both remarks by defining some kind of filtered version of the Yodo-Kato stack. And this will play a role in, but I think this will be explained maybe by Max in his lectures. But I wanted to give these examples because this stack will play a role in my discussion of the prismatization of rigid spaces. Okay, that's all for today.
had a theorem that if x to y is smooth, then the reduced Dronstadt stat is homologically smooth. So which category was your x and y living?
They can be arc stacks.
So there is a notion of smoothness.
Yeah, it's just something which locally is like composition of like some étale map to some affine relative affine space. Yes. Sorry.
But a smooth morphism of gradient spaces. Smooth.
Yes. Well, no, you have to be slightly careful with this just because we work in this Berkovich setting. So, like this D that I wrote over there is not smooth anymore. Yeah, so it's proper, but it's not smooth. So it's kind of a little bit switched with. So that's why I always want to restrict to partially proper or work with divergent spaces. But yeah. So rational localization is not smooth.
The smooth map of dagger things will be okay.
Yeah.
So, like if you have some rigid space, let's say partially proper, then the map given by rational localization is not smooth. You're saying?
No, it's not. Yeah.
If you instead of saying that f is less than or equal to 1, if you say that it's less than 1.
Say that again.
I mean, if you say that f is less than 1, so if you say that f is less than 1.
Yeah, then that's good. Yeah. Like open this would be smooth, for example. But
so I guess the next talk will be on Wednesday. This is the announcement location. Let's thank our juice during.
yeah, well.